Welcome to our project overview of our designed game of Yahtzee for our spring 2024 Senior Design 2 class. This was made by Brian, Emma Louise, Bryson, Luke, and Aditi. Our motivation for this project was based on our work in Senior Design 1 when we worked on Connect 4 and Tic-Tac-Toe. By doing so in Senior Design 1, we really enjoyed the projects and how engaged they made us, and that's how we ultimately chose to work on Yahtzee. What is Yahtzee? Yahtzee is a popular dice game played with 5 dice. The objective is to score points by rolling a certain combinations of numbers across multiple turns. Each player takes turns rolling the dice up to 3 times per turn, trying to achieve specific combinations like 3 of a kind, 4 of a kind, a full house, straight, and the elusive Yahtzee, 5 of a kind. After each turn, the player chooses which category to score their dice based on their roll. Each category can only be used once per game. The player with the highest total score at the end of all turns wins. It's a game of both luck and strategy, as players must decide which combinations to aim for and when to press their luck with additional rolls. The goal of this project is to create a game of Yahtzee that a person can play against a computer. It is made simple and easy for the user. We are trying to design Yahtzee completely from scratch.
The first problem that needed to be solved from the hardware perspective was how to roll the dice. Our solution is to have 5 separate dice chambers where each one is controlled separately. In each chamber, the dice lay on a felt padded tray, which rests on a small lip to keep it from falling. Underneath the tray is a 300 RPM rated 12-volt DC motor. Attached to the rotor shaft is a 3D printed blade, which knocks the bottom of the tray when the motor is turned on. The fast knocking of the tray gets the dice to pop up in the air and land on a random side. The chambers themselves required a significant amount of prototyping in order to produce a reliable and consistent result. The chambers themselves are each 2.5 by 2.5 inches wide and have a small cutout along the edge 1.5 inches from the top. The chambers were arranged in the zipper orientation to condense the image the camera would need to read. The adjustments that needed to be made were the tapered corners of each cell and an arc cut out between the 3 cells in the top row. The tapered edges force the dice back towards the center of the circle when the tray is bouncing, not allowing the dice to get caught in the corners where the camera cannot detect its value. Similarly, the arced out cuts along the top of the cell wall will allow the camera to view the inside edges of the outermost cells on the top row. Finally, removable guards were installed to keep the trays from sliding out of the chamber, but also let the user take them out if needed. The next problem that needs to be solved was a way to control the DC motors from the Raspberry Pi output pins. Our solution is a simple transistor circuit where the motor is connected in parallel with a flyback diode, and between the positive end of the power supply and the collector of the NPN transistor. The GPIO pins from the Raspberry Pi are connected in series with a 330 ohm resistor and terminated at the base of the transistor. When the output signal from the Raspberry Pi is turned high, the transistor allows current to flow, turning on the motor. The project required the circuit to be repeated for a total of 5 times, 1 to control each of the motors. The final part of the hardware design was the camera stand. Since the program software requires a fixed camera position for operation, it is essential to design a sturdy structure that will allow for consistent camera readings and would not move during gameplay. Our design involves 2 posts, 11 inches tall, with widened feet to ensure stability. A bar spans across both of the posts where the camera rests. The camera slides into an oval-shaped slot above the game board and is secured with no movement.
In order to generate basic GUI code, TK Enter Designer was used. This program utilizes Figma, which is an online web application to drag and drop widgets in place. This is then sent through the TK Enter Designer program to generate TK Enter widgets in Python. From there, we were able to further edit the widgets, but this program made the creation of the widgets easier. We used this as a starting point to create the user interface. This diagram shows how we decided to lay out our user interface. Starting from the upper left, we have 2 columns, each of which display the user scores and the computer scores. They are organized by categories on the far left of the screen. Next to these columns, we have buttons that the user can press to determine which category they would like to save their score in. On the upper right side, there is a text box that will tell the user the current instructions, such as whose turn it is or when to choose dice they want to keep. Below this are pictures of die faces that update according to what the camera is able to detect. These update for both the user and computer turns. Below these are the keep buttons that the user clicks when they wish not to re-roll dice on their next turn. Lastly, the roll button is pressed by the user whenever they decide to re-roll their dice. The start button is pressed to start the game. Both the start button and the keep buttons are disabled when it's the machine's turn. We utilized Python version 3 and created 4 main Python files to store our functions in. Display controls the basic gameplay and keeps track of things like turns and scores. It is also where the main function is called and where all of the code is generated from TK Enter Designer is stored. When it's time to roll, functions and motor control are called to roll the physical dice. With the use of GPIO pins, we are able to communicate with the 5 motors. Determine Next decides which dice to re-roll based on the current game score and the dice that are available. The functions in this file are used by both the computer and for the user when suggesting moves. Save Score selects the best place to output the score given the current scores, dice values, and the dice that will be re-rolled. The functions in this file are also used by both the computer and the user.
So for our software design solution, we have kind of 2 main things. We have the code related to the camera and the motors. The motor code is very simple though, so I didn't really talk about it too much, but I'll explain just a little bit of that. Motor control is just using the GPIO library within the Raspberry Pi. And so we turn on certain pins to trigger the motors turning on or off and the power supplied just from a 12-volt battery supply. But the actual software code that is a little more intensive is the camera and the game algorithm. So the camera, we found some pre-existing code from GitHub that captured the dice numbers in real time. And the main way it did this was through a tool in OpenCV. There's different masks that you can apply to images. And the one that worked the best for dice was the blob mask. So basically, it would find blobs of high contrasting colors, big or small. But it was specifically good with the small pips of the dice. Yeah, and that just allowed us to extract the dice based on certain circumference in the image. And then we read that in to an array called dice, and then that dice was used wherever else in the code we needed. So our game algorithm, that was self-generated. We looked at some stuff online, but it was all like graduate level research papers. And so we just decided to base it on our own experience playing Yahtzee. Basically like, oh, it's a lot of if statements. So it was basically like, oh, well, if we have a small straight, like, let's just check if it's over 20, not over 20, then we'll just take a lower category. Just kind of providing some general guidelines. But with our general guidelines, it allows for complete automation from the machine side. So a player can play a complete game against an autonomous opponent to completion. It also provides the recommended dice to reroll or keep. This is from the function of the machine. Like we just needed the machine to know when to keep dice or when to not, and go for bigger scores, or just be content with what it had and save it in that score box. And yes, that's some of the software design functionality. And so for our performance analysis, this is just kind of an overview of how the project went. So I think overall, we did a good job of managing our team dynamics. We were split up with 3 electrical engineers and 2 computer engineers. And so that allowed us to delegate tasks. And me and Emma Louise weren't going to be working on the same things as Brian, DD, and Luke. And so that really allowed even me and Emma Louise to split up the code portions a lot, for her to work more on the GUI and for me to work more on the camera and game algorithms and the hardware integration kind of stuff. We also implemented an iterative design, specifically with our dice holding structure. That went through many designs, mainly with the separators in between the dice. We found some issues with the camera where we had to fill it and lower the inside separator so that the camera could recognize things better, And, yeah, it was just effective communication. We made a group chat immediately, once we got our group together, and yeah, we just held each other accountable, tried to get stuff done on time, and it led to a pretty successful project.
Some of the strengths our project has is that overall, a user is able to successfully play a game of Yahtzee against the computer, which achieved our main goal. All 5 dice are able to roll random values for both the user and the computer. The GUI we have designed makes the project very user-friendly, and all of our physical components have very polished designs with minimal exposed wiring. Some of the weaknesses our project has is that only one person can play against the computer at a time. An improvement that could be made is allowing multiple people to play a game against each other. The game logic we have is good, but could be improved to make the computer a harder opponent to play against. The amount of noise our system makes could also be improved, and our system could be physically condensed further to make it more portable.
That'll get us a C and a B. Unless you guys want these washers, I'm just gonna let you go. Once it let's go. I don't know. I'm seeing me out of going before. I want that. That's good. It's like whacking into the floor. Yeah, whenever it beats that, it would go. Yeah.